Hello friends and welcome back. In this video we'll be talking about the concept of central forces or central potentials, which is key to a lot of applications in physics and in science more in general, and definitely a key applications for gravitation, Newton's law of gravitation. And we start by defining the nomenclature. What do we mean by central force or central potential? So central forces are the ones that are directed along the line joining the two objects that are exchanging this force. Line joining the two objects. So if and indeed, in the case of two masses interacting gravitationally, we said that the force between them is precisely directed along this line, and so this is there's no doubt that gravity is a central force. Okay. That Newton's law of gravity is that of a central force. And this implies, by the way, that the corresponding potential energy or potential is also central, but the meaning for potential energy is that then the potential energy only depends on the distance between the two objects. In a more general case, you know that you can always write a potential energy that depends on the position vector, but it might depend non-trivially on the coordinates x, y, z, whereas writing this implies that the only thing that matters when I look at the potential energy between in a system of two masses is not the precise relative location, but only the relative distance. To give you an example, if the mass was located here at the same distance, this implies the different forces but same gravitational potential energy, because the distance is the same. All right. So whenever you have a force field or a type of interaction that is directed along the line joining the two bodies, and or, because they are one and the same statement, and or a potential energy that only depends on the magnitude of the displacement, so on the distance, then you have a central force or a central potential. Examples of this are, well, as we said, gravity is definitely a central potential. Electrostatics, so Coulomb's law, which by the way is extremely similar to Newton's law of gravitation, is 1 over r squared as well. And elastic force, so Hooke's law, not Coulomb, which you probably remember from intro physics, that also, remember that K was minus K, F was minus Kx, and that is precisely directed along the line that joins the equilibrium point and the displacement, well, the location of the mass that's attached to the spring. So that is also a central force. One of the most important properties of central forces and central potentials is that angular momentum, which, okay, it's still quite a mysterious concept, but it will become clearer and clearer as this course progresses. And for now, let's just, well, let me write two fundamental things. One is that angular momentum is conserved. So there's a law of conservation of angular momentum that is not unlike conservation of energy and conservation of linear momentum, which we already have talked about. And for now, accept just to for me to define angular momentum as follows. We tend to denote it with L. You'll discover in a couple of weeks that it's actually a vector, but for now, let's just use its magnitude. And this is the absolute value of this operation, which I'll talk about in just a second, just now. Or M, R, so P is momentum, and V. So if you take an origin of your reference frame, and you take an object of mass M moving at with a certain velocity V, with this being R, the position vector, then there's this operation called cross product, or vector product, which gives you the value for the angular momentum. Now, what does this operation look like? Well, the magnitude, let's say that if I take, in a slightly more general sense, I take a vector A and I take a vector B with an angle theta between them, then the absolute value of A cross B is the magnitude of A, the magnitude of B, and look at this, the sine of the angle between them. Not the cosine, like in the dot product. See, dot product used to have cosine here. This has the sine, okay? And actually, if I really want to be precise, I should take this absolute value as well, because sine, then, yeah, yeah, if you have plus, so if you change A and B, you would get a minus sign, which is very true and important when you deal with the vector form of that product. But anyway, but not at this stage. But since I've mentioned this, I hinted this a little too strongly to ignore it. The actual operation I need to mention, the operation of cross product, this gives me a vector, okay, and the magnitude of this vector is the absolute value of this combination, okay. Further details will be given in a couple of weeks, but for now, let's sit for a second with this new concept of angular momentum, and it has this expression that you can then calculate using this operation of cross product or vector product. And so actually let me zoom out for a second. And so applying this definition of cross product that I gave you, we see that the value of angular momentum of an object of mass m that is moving, that has position r and velocity v, is none other than m r v, and the sine of the angle between the vector r and the vector v. So in this particular situation, it would be this theta here. All right. Now, this object throughout whichever motion that only happens in a central potential, this is always the same value. and it's extremely important, and we will discuss it in many places in this course. All right. Let me draw this diagram once again, because this is where it starts getting really interesting when it comes to gravity. So let's take again this center, this origin of my reference frame. I have my vector, position vector, that separates the origin to an object of mass m, and I said that this object is moving with velocity v. All right. And we said, okay, so I define this value of L as m r and then v times the sine of theta, where this is theta. And allow me to see, in the spirit of polar coordinates or angular variables that we talked about already, let me choose a radial reference frame, actually with that's centered in the origin here, where the two axes are, actually this is the other way around, are the radial direction and the tangential direction. So where this component is the tangential velocity and this component is the radial velocity, right? This is some construction that we've done last week as well. And so you may notice that this combination here is equal in magnitude to, well, I'll give you a second actually, to the tangential or the radial velocity. Let's see if you can get it. Well, I hope that you stop the video or stop it now, and that after resuming the video, you agree with me that this is the tangential velocity, right? Remember what the tangential velocity was equal to when I wrote it in polar coordinates? Well, this was simply equal to r, the distance from the center, and phi dot, or r omega, if talking about angular velocity, right? So this in turn gives me this expression that's very useful for the angular momentum, which is m r squared times omega, or equivalently m r squared phi dot. As usual, dot is a derivative with respect to time. Okay. Now, why is this useful? Check this out. Let me write the expression for the total energy of an object in a central potential. This will be equal to 1/2 mv squared plus the potential as a function of r. And you remember probably from the previous week that this is just, Pythagoras. This is v radial plus v tangential squared plus u, which is a function of r only. And moving this here for a second. And so we can write this with the exact expressions for radial velocity and tangential velocity, which we expressed last week, which is r dot squared for radial velocity, and we just talked about it, r squared omega squared for tangential velocity, plus u of r. Now, this is in principle, well, it gives me this combination where the rate of change of the distance between the objects and the angular velocity times the value of the distance, they behave they have this relationship. But we can do more applying the conservation of angular momentum, because if we see from up here above that the value of the angular momentum is m r squared omega, then this implies that omega is simply the value of angular momentum divided by m r squared. I can plug this into this expression to rewrite the total energy in the extremely convenient form 1/2 m r dot squared plus angular momentum squared divided by 2 m r squared. Double check the calculations if you don't believe me. Plus potential, which is a central potential. Wonderful. So this is a new but completely equivalent expression for the total energy of the system that is looking specifically at the rate of change of the distance and the distance itself. And you see there's no angular variable anymore. There used to be angular velocity here, which told me how quickly the angle phi was changing, phi being, this would be the angle phi. And now it's vanished. See, it seemed like I used to have two variables that dictated the behavior of the system, but actually it's only one. R alone is enough, essentially. And we'll see just now how this changes the picture. Let me rewrite this expression on a blank page. The total energy is equal to 1/2 m r dot squared plus angular momentum squared, which is a conserved quantity. So that's a number that is the same throughout the evolution of the system, over 2m r squared, plus whatever central potential I had. All right. The combination of these two terms here is what is commonly referred to as effective potential. So U effective, which is the original potential that I had depending on whatever interaction I have, I'm considering an L squared over 2m r squared. Why is this called effective potential? Because essentially what this law of conservation of energy is telling me is that I have a one-dimensional problem, basically, in the sense of r, the distance, is the only real variable that matters to do energy conservation, with an effective potential energy which is slightly modified from its sort of naive or bare interaction with this additional term that depends on the angular momentum. Let's see what this implies. Take, for example, the potential energy for gravity, which, as we said, is minus g m divided by r. And we had a plot for this function. Actually, let me draw it like this. That said that the gravitational potential energy was like this. This was U for gravity as a function of r, right? And we, for example, we use this type of plot to discuss, escape velocity and energy consideration. And if this is r and this is u, so what is the effective potential, however? So this correction, L squared divided by 2m r squared, can I plot it on the graph? This would be, it's a 1 over r squared term, so something like this. It's positive, importantly, and positive, if you remember, this is, let me write it down, positive and repulsive. Because force is always pointing sort of to lower values of the potential energy, a positive, actually positive and repulsive are not necessarily the same thing, but negative slope and repulsive are the same thing. So please, this is not an equal sign, but it's an and repulsive. So please don't quote me well. Positive, very true. Repulsive, also very true. They are not the same thing. Repulsive means negative derivative. So u prime less than 0. Okay. But so what is then the sum of, so this would be L squared divided by 2m r squared. The sum of the two, which is this total effective potential, let me use a slightly thicker, would be something like this. All right? That's the effective potential that my that my object lives in, as it were. We notice that at large values of r, you still recover the effective potential going to 0, because both 1 over r and 1 over r squared go to 0. But at low values of r, at some point 1 over r squared, which is in this denominator, decreases more quickly than 1 over r, which is instead in this denominator. And so at some point the positive contribution dominates, inevitably. And what emerges is this picture that makes it way more transparent to look at bound or unbound systems. Because look at this. For a bound system, which we defined as a system where the total energy is negative, it means that I have a value of energy somewhere here, for example. And the condition that the potential energy or effective potential energy can never be, is always less or equal than the total energy, because the kinetic energy is always non-negative, implies that there's a minimum and a maximum value of distance that my two objects can have between them. Right? This wasn't so obvious if I didn't consider the effective potential, but it is so transparent now. So essentially, the system is bound, and two objects that have a specific value of total energy that is negative, and it's this value, E total, and a specific angular momentum, which is also a conserved quantity, they will be oscillating back and forth between these two values of distance, between a minimum value and a maximum value. That's so interesting, right? On the other hand, an unbound system where the energy is either 0 at the minimum, or a positive if I go even further. For example, here, there is no maximum value for radius, so this is infinite, but there is actually a minimum value even with positive energy. And that is extremely interesting, because if you only look at the graph of the gravitational potential energy, you would assume that you can keep getting closer and closer, and simply the potential energy gets more and more negative. But actually, the conservation of angular momentum dictates that you can get arbitrarily close and still conserve angular momentum. So let me maybe zoom out and write this down because it's really, really important. The conservation of angular momentum told me that there's a correction to the potential energy such that there's a repulsive term at low radii. And so there is a minimum distance between objects that is compatible with all the laws of physics. There, I cannot get arbitrary close to zero, or the two masses arbitrarily close to one another, because otherwise I'd violate physics, and that is so interesting. To conclude this part, let me just rewrite for a second again that the effective potential is the original potential plus this term L squared divided by 2mr squared. And so, given the relationship between force and effective potential, the effective force, right, it's the derivative of the effective potential over dr with a minus sign. And so it's the original force, so the central force that we talked about, minus the derivative of this term, L squared divided by 2mr squared. And I hope you can see that this is the original force. Let me just remove the vector sign. The original force as a function of r, and then plus the derivative, which is L squared, the 2 and 2, so mr cubed. And this is again why this is where I can see the properties of this extra term, which is repulsive, because this is positive. The value of the force is positive, meaning it's pointing to the right, to bigger values of r. And it's large at when r goes to 0 for small distances. Let me rewrite this arrow. So it acts as a repulsive barrier at small radii that prevents objects from just getting arbitrarily close to one another. Very nice. All right, look forward to applying these concepts to gravity in a more interesting applied manner. But for now, thank you so much for watching, and I'll see you soon.